Block ciphers are the workhorse of encryption on the internet today. And no, they have nothing to do with Bitcoin. Also, crypto is short for cryptography, even when you're talking about cryptocurrency. In this video, we're going to talk about block ciphers. They're the tool that we use to encrypt the bulk of the data that is being transmitted across the internet. If you haven't already done so, go back and check out our videos on semantic security and classical ciphers. In future videos, we'll look at other more complicated ideas like how we detect whether a ciphertext has been modified, or how does the block cipher even get the key in the first place. But right now, our focus is just on how is data encrypted on the internet. A block cipher is a cipher that acts on fixed length chunks of data, also known as blocks. Each block is encrypted individually. So as we'll see, we need to take some special care to do it right. As we discussed in previous videos, a cipher is a family of three functions. In a block cipher, the key generation function accepts a key length parameter and produces a single fixed length, randomly chosen symmetric key. By symmetric key, I mean it's the same key that will be used to encrypt as decrypt. Now there's an important parameter in a block cipher. It's called the block length. We denote it as the letter B. The block cipher encryption function accepts a B-bit plaintext as input, as well as a K-bit key. And it produces a B-bit ciphertext. Notice how the plaintext and ciphertext bit lengths are the same. Decryption, of course, is just the undoing of the encryption operation. It's going to accept a B-bit ciphertext, a K-bit key, and give us back a B-bit plaintext. Before we can start talking about specific block ciphers, we need to form an understanding of what it is we're actually trying to do with a block cipher. Let's begin by asking the question, what is a block cipher and what does it look like in a perfect world? The first property we need is for the encryption function to be injective. That means every plaintext maps to a unique ciphertext. This is obviously necessary to guarantee unique decryption. If two plaintexts could encrypt to the same ciphertext, it would not be possible to uniquely recover the plaintext upon decryption. The encryption function also needs to be surjective. Every ciphertext decrypts to some plaintext. This is also necessary for unique decryption. Putting these two properties together, injection and surjection, gives us a property called bijection. That means that every plaintext is associated with a unique ciphertext and vice versa. So essentially what we've created here is a function that is a permutation or shuffle of B-bit strings. If we have a B-bit block, that means the plaintext space involves 2 to the power of B different possible input plaintext messages. Similarly, we have 2 to the power of B possible ciphertext messages. So if we're shuffling 2 to the power of B elements, there are 2 to the power of B factorial many ways this can be done. So you can think of the key as being something that chooses a particular permutation out of the permutation space. However, the key space for a K-bit key is only 2 to the power of K possibilities. Now typically 2 to the power of K is going to be much, much smaller than 2 to the power of B factorial. So that means there's going to be a large number of permutations that just simply aren't possible in a particular cipher. But if the cipher is designed well, similar looking keys will select vastly different looking permutations. So you can kind of think of a block cipher as being like a large collection of code books. A code book is a book that on one side has a list of plaintext elements and on the other side has an associated list of ciphertext elements. To do encryption, you're essentially going and finding your entry in the codebook and then looking at what the ciphertext should be. So which codebook are you using at any given moment? Well, that's going to be a function of the key. And the key is a secret. So an eavesdropper has the ability to reconstruct this family of codebooks. The problem is that there are so many of them, they won't know which one you chose. Okay, so now here's a question. If a block cipher is designed to only act on a small slice of bits at a given time, how do we encrypt a large message? A modern block cipher will typically encrypt 16 bytes at a time. So how do we encrypt an entire YouTube video? So this brings us to the notion of something called a cipher mode of operation. A mode of operation is the method that we're going to use to take a block cipher and combine it to encrypt a large amount of data. The simplest mode of operation is called the electronic codebook mode. It's very straightforward. It takes the plaintext and divides it up into individual B-bit blocks and encrypts each one separately using the same key. So imagine, as an example, we had a little tiny itty-bitty little 2-bit block cipher. Remember, when you pick a key, it's going to effectively select a particular codebook to use. So using this particular key, and therefore this particular codebook, the block 00 will encrypt to the ciphertext block 11. The plaintext block 11 will encrypt to the ciphertext block 10. Each successive block is encrypted in the same way. You take the plaintext bits and you go look them up in the codebook and replace them with the ciphertext bits. Now, if you were doing this with a 128-bit block, your codebook would have 2 to the 128 different entries. This codebook is so large, you could never write it down on paper. In fact, 2 to the 128 is starting to get close to the number of atoms in the observable universe. So there is no actual codebook, it just effectively exists through the encryption function. Okay, but wait a second. If encryption is just simply a matter of taking blocks of data and then looking up the ciphertext in the codebook, then we have a problem, because every plaintext block will always encrypt to the same ciphertext block for a given key. So I'm going to show you an example of this limitation in practice. I'm going to take an image and encrypt it using ECB mode. SE4472 is the course code of this course that I teach. As you can see in the hex editor on the right, the file has a lot of structure. All of those FFFFFF hexadecimal bytes represent sequences of white pixels corresponding to the top of the image. Okay, so we're going to go ahead and use OpenSSL to encrypt this image using ECB mode. So here's what we get. Every 128-bit block of white pixels, every 16-byte block, encrypts to some kind of random-looking sequence of numbers. Those random-looking numbers, in turn, will display as a sequence of random-looking pixel colors. Okay, but now you see the problem. Every time we encrypt a block of white pixels like that, it will always go to that particular pattern of colored pixels. And as you can see, that pattern repeats over and over and over again. So here's what the encrypted image looks like if you try to view it. Oops! Okay, so is ECB mode secure under the eavesdropping attack? Obviously not. Clearly, you can win the eavesdropping attack game quite easily. All you have to do is create 2 different messages that contain structure that is larger than the block length. ECB mode doesn't disrupt that larger scale structure. Now, given this fact, you can imagine that there really should be no reason that anyone is using ECB mode ever for anything. This is the 2020s. Who honestly is going to use ECB mode at this point? Unfortunately, this kind of rookie mistake keeps cropping up, most recently in a study done by the Citizen Lab of the Zoom platform. They were using ECB mode to encrypt a video feed. Okay, so we gotta do something about this. We need to think of a way to somehow combine these different blocks together to break up the large-scale structure in the plaintext. And while we're at it, what if there was a way to make it such that if I encrypted the same message twice, I would get different ciphertexts? So this brings us to one of the more well-known cipher modes of operation called cipher-block chaining. The idea of CBC mode is to compute the bitwise exclusive OR of every plaintext with the ciphertext from the previous block. This combined value is the thing that is then put into the encryption function. So as you can see in this example, even though the plaintext has a lot of large-scale structure, that structure gets broken up with this feed forward of the ciphertext into each successive encryption. All right, so what do you do on the first block? There's no previous block of ciphertext to feed forward to use. So there we use something called an initialization vector, or IV. We use the IV to get things going. Okay, so we're onto something here. We've got something that will take a very structured plaintext and create a very random-looking ciphertext. So when it comes time to decrypt, what we're going to do is take the ciphertext and run through the decryption function. That's going to give us the XORed pair of plaintext block with the previous ciphertext block. But because the XOR operation is symmetric, we can XOR out that previous ciphertext block because we know what it is. And therefore we can recover the plaintext block. So you'll notice from this diagram that the vertical arrows have reverse direction. Ciphertexts are now going through decryption functions up to the plaintext. However, the ciphertext feed forward arrows continue in the same direction as in the encryption function. Now we come to a really important property called randomized encryption. As you can see in this example, if we encrypt the same plaintext twice using the same key, but we use a different initialization vector, the ciphertexts will look totally different from each other. As we'll see in a moment, this is going to help protect us against the chosen plaintext attack. Now there's a few important points to make about the initialization vector. The first is that the IV is not a secret. In fact, it is sent along with the ciphertext through the communication channel. Now for the IV to be effective at preventing the chosen plaintext attack, we need to make sure of two things. The first is that the IV is never reused. The second is that the IV is also unpredictable to the attacker ahead of time. Next up is a mode of operation called counter mode. Counter mode is a little bit different than CBC mode. You're never actually putting the plaintext through the encryption function. Instead, what you're doing is encrypting a counter and XORing the result with the plaintext. So as you can see in this example, if we began with the initialization vector 10, we would start in the first block by encrypting 10 and taking the result and XORing it with the plaintext message block. In the second block, we would take the initialization vector 10 and we would increment it by 1 to 1, 1. So we would encrypt 1, 1, take the result and XOR it with the second plaintext block. Similarly, for the third block, we take the 1, 1 and increment it by 1. It rolls over to 0, 0. We encrypt that. We take that result and XOR it with the third plaintext block, and so on. Okay, here's the cool part. Decryption is exactly the same as encryption, except we reverse the inputs of the XOR function. We take the counter, we run it forward through the encryption function, and we take that result and XOR it with the ciphertext to give us back the original plaintext. So you'll notice that decryption actually involves the encryption function of the block cipher. Now, relative to CBC mode, counter mode has a couple of advantages. The first is that it's not vulnerable to these padding oracle attacks, which we're going to talk about in future videos. It's also simpler to implement. You only need an encryption function. And because each block is processed individually, you can parallelize the computation. Also, because the encryption doesn't actually involve the plaintext, you can compute it all ahead of time. On the other hand, counter mode is not suitable for smaller block lengths. Okay, let's return to CBC mode for a moment, and let's see how it does in the chosen plaintext attack game. Remember, at the beginning of the game, the guesser is allowed to make encryption queries. They're allowed to ask the challenger to encrypt plaintext that they choose. So in this example, the guesser submits the plaintext 00 to be encrypted, but because we're using cipher block chaining, the challenger selects a random initialization vector and incorporates that into the plaintext before encryption. So if the guesser submits the plaintext 00 again, the challenger is going to pick a new initialization vector and rerun the encryption. In both cases, the ciphertexts are going to look different even though the plaintext was the same. Finally, when it comes time to create the challenge plaintext, the challenger is going to flip a coin and pick one of the messages to encrypt. So even if the challenger picks 00, which was already encrypted multiple times during the query phase, once again they're going to pick a new initialization vector. Remember, one of the requirements is the initialization vector should not be reused. It's hard to see in a small 2-bit example, but if we were using 128-bit initialization vectors, it would be overwhelmingly likely that the challenger would select a new initialization vector that had never been chosen before. So the challenger will select a fresh initialization vector and create a fresh ciphertext. That challenge ciphertext is returned to the guesser, and now they're on the hook to guess which message was chosen. But because new initialization vectors were chosen every time, encrypting the plaintext 00 results in different ciphertexts every time, which means the guesser is given a new ciphertext that they haven't seen before, even though they've submitted multiple encryption queries for the plaintext 00 already. So what that means is that the guesser is overwhelmingly likely to have not seen the challenge ciphertext before, and therefore they won't know what to pick. So randomized encryption is the method that we use to defeat the chosen plaintext attack. Okay, so here's a bit of homework. Prove that the cipher-block chaining mode of operation is not secure under chosen plaintext attack if the initialization vector can be predicted ahead of time. So for example, imagine that the challenger understood that they could not pick the same initialization vector twice. And as a way to ensure that, they incremented the initialization vector by 1 every time. So when you make an encryption query, you see the initialization vector as it is right now, and if you know that it's going to be 1 more later, you can exploit this fact to negate the effect of the initialization vector on the ciphertext. Remember, the initialization vector is combined with the plaintext using XOR, which is a symmetric function that can be easily undone. Okay, now finally, let's just take a little peek inside a real block cipher, the Advanced Encryption Standard, AES. AES is the most commonly used block cipher on the internet today. At a high level, the AES cipher uses a 128-bit block. That means it accepts 128 bits of plaintext and produces 128 bits of ciphertext. The key can either be 128, 192, or 256 bits. The plaintext is combined with the key through multiple passes of something called a round. Rounds are identical at each stage, and the key is changed at every round using something called the key schedule. AES uses 2 types of operations. Operations that either act on bytes, 8 bits at a time, or operate on individual bits at a time. The first operation is a byte-wise substitution. A byte, 8 bits, has 256 possibilities. So the substitution lookup table, called the S-box, has 256 entries. Now there are 256 factorial possible S-boxes that you could create. Instead of designing some random permutation, the AES designers chose an algebraic relationship. The output byte is the algebraic inverse of the input byte in what's called a Galois field. And for good measure, they also add a constant value. So in this step, you act on every single byte individually. You go and look up each individual byte in the S-box lookup table to find the corresponding byte and replace it. S-boxes are designed to be highly nonlinear. The idea is that we want a small change in the input to induce a very large and catastrophic change in the output. Or in algebraic terms, if you wrote out the Boolean equations, you would want to see a lot of terms that were products of all the input bits. The next step is called shift rows. We take all of the 16 bytes and arrange them as a 4x4 square. And for each row, we apply a circular shift. The top row is untouched, the second row is shifted by 1 byte, the third row is shifted by 2 bytes, and the bottom row is shifted by 3 bytes. The third operation is called mixed columns, and here we're going to apply Galois field arithmetic again, this time using matrix multiplication. This time, instead of applying it to the rows, we're applying it to the columns. The shift rows and mixed columns operations are designed to provide a property called diffusion. What we're trying to do is get the variables that appear in the algebraic equation to spread out. And finally, in the last step, we take the round specific subkey and we XOR it with all of the bits that came out of the mixed columns step. Finally, the output of this process is fed into the input of the next round, and the process continues. Now, for most people, you can treat AES like a black box. All you need to know is that if you do your job, it will do its job to protect you. And your job is to pick a random secret key, a randomized and safe cipher mode of operation, and an unpredictable initialization vector. All right, that's it for this video. In the next video, we're going to talk about something called hash functions. If you enjoyed what you saw here, don't forget to click like and subscribe, and we'll see you in the next video.